Today we're going to introduce piecewise functions. Piecewise functions are also sometimes called, I call them Franken functions, because they're made out of a bunch of different functions stapled together. They're not too bad. It's at least all of the stuff we've done before. But it's just kind of putting them together that's kind of the tricky part. A couple of things to keep in mind. I've got a piecewise function listed here for illustration purposes. This is more complicated than anything that we'll have to make. Notice right here we have a gap. That's totally fine in a piecewise function. It doesn't necessarily have to look like one continuous line. You'll also notice that we have linear components here, something kind of like that line. We also have some exponential components, like here. And you'll also notice we have a semicircle, which we haven't talked about how to figure that out either, but we are more than capable of drawing them into a piecewise function if we need to. The only things a piecewise function cannot include is we can't have vertical lines, and we can't have overlaps. So I'll just draw out a quick little example of each of those. So no vertical lines, and we can't have an overlap, or one point going to two different places at the same time. Otherwise, it would not be a function. So we have something that kind of looks like this, maybe like stops there, and then this part comes over like this. That wouldn't be a function because you'll notice here we have two different y-intercepts, and that's a problem. So piecewise functions, no vertical lines, no overlaps. Other than that, pretty much anything is fair game. You'll notice some of your problems ask you to just come up with a piecewise function without a graph for it, and you are more than welcome to doodle in anything like that. Let's go ahead and write out the rules for graphing one of these things. First, you'll notice a piecewise function usually has the form of this. It's going to be f of x, the name of the function, is equal to some kind of fancy scroll thing. That's just our way of saying that these are all connected together. And we have three different functions, or perhaps more, or perhaps less, in there. And then we'll have what's called a row of conditional statements. They can be written as inequalities or interval notation. So I have them both ways on the assignment so you can take a look at them. I'm okay if you write them either way. That will be fine. We can go ahead and look at this function down here. This is number 1 on your homework. You'll notice we have two different linear functions in here. We have our first linear function, negative 4x minus 2, and our second one, 3 halves x plus 5. And they kind of overlap here, except they don't, because we have these conditions. So for numbers smaller than negative 2, we consider the top function. For numbers bigger than negative 2, we consider the bottom function. So for example, if we wanted to consider x is equal to 1, we would plug that into the bottom equation here, because 1 is bigger than negative 2. Similarly, if we wanted to consider x is equal to negative 6, we'd have to use the top equation, because negative 6 is smaller than negative 2. And graphing it is very similar, follows similar rules. So here is how I would go about graphing something that looks like this. First things first, draw in your axes. I didn't give you graph paper on this assignment on purpose because I think it's helpful when you're doing these to be able to have a lot of control over the shape that they're going to take. And so I'm going to give you a little bit of free rein on there. So the first step is drawing your axes. I'm not going to even list that as a step. I think it's fairly self-explanatory. The first thing that you do after that is take a guess. Draw in what you think the shape is going to look like. Take a guess. I find that it's very helpful to just take it from what looks like a bunch of scary symbols, and once you write it out, it looks very familiar to us. It's all stuff that we've done before. So let's go ahead and just take our guess. So we have negative 4x minus 2. Well, that's going to be a pretty steep straight line. It's going up something kind of like that. And then we have 3 halves x plus 5. That's going to be something, it's like 5's right there. It's going to look something kind of like that. And we're going to have two different numbers. Sorry, scratch that. We have two different lines here. We can't have both lines at the same time. So we have to reconsider on what part do we care about. So we only care about the negative 4x minus 2 up to negative 2. So if we declare this point here as negative 2, oops, that's not what I want to do. Then we only care about the left half of the line, right up till negative 2. Similarly, we only care about the other line on the other side of negative 2. The reason we know that is it literally tells us when x is less than negative 2, that's when we care about the negative 4x minus 2. When when x is bigger than negative 2, we care about the 3 halves x plus 5. All right, so we've taken our guess. It helped us see it a little bit. The next thing we're going to do is sketch in our changing points. Sometimes we have more than one of them. In this case, we only have one. We know that the function changes at negative 2. So let's go ahead, and I'm going to put in like a buffer. It's going to be a dotted line. It's imaginary. It's not going to be something that's actually part of the function. But I'm going to just put that dotted line at x equals negative 2 to let me know that at that point, the function changes. It's not really there. You don't have to include it in the final picture. I would honestly recommend doing it in a different color, like a colored pencil, so it doesn't confuse you, but you don't have to do that. It's just my way of trying to make this look as simple as possible. All right, so now we've put in our changing points. The next step we've got to do is put the parts of the function on either side of your changing points. Okay, so we know that on the left side of our negative 2 changing point, that's going to be the negative 4x minus 2. We know that because we're looking for the values of x smaller than negative 2. And for the values bigger than negative 2, we use 3 halves x plus 5. We know that that's where that's going to be. All right. Now that we've figured out what's going where, go ahead and graph. So let's go ahead and we start this line at our y-intercept at -2. Our slope is -4. So we rise up 4, go over -1. Similar thing again. Up 2, 3, 4. And over. And then from there we can connect the dots. I'm only going to go up to that -2 line. Even though I started at the y-intercept, because that's what we had, I'm only going to go up until -2, because after that point, we don't know what we care about. Well, we do know what we care about. It's just the other function. So we'll stop there. All right, so now that we've graphed that part, let's go ahead and graph the next part of the line. 3/2 x plus 5, so we're going to start at 1, 2, 3, 4, 5. We have our slope, our 1, 2, 3, 1, 2, 1, 2, down 1, 2, 3. We can graph that line. And it's not that concerning that they don't connect together. However, it would still pass the vertical line test. Well, sort of. We have to do the last step. We have to check the changing points. So notice that if we included -2 in both places, then we would have an overlap, and that would be a problem. So you'll notice when we wrote out the problem that this one is less than but not equal to, and this one is greater than and equal to. So therefore, the -2 belongs to that part there on the 3/2 x plus 5. To be really complete about it, we would go ahead and make a bubble, an empty bubble on the other function. Pay a little bit of attention to this, but not a ton of attention. Simply put, it's not something I'm going to test you that much on. You should be able to, okay. You should be able to figure it out, but I'm not that worried about it. All right, I'm going to go ahead and do another example. We're going to go ahead and try number 3 from your homework. Number 3 has a typo that I'll explain here in a second. I'm just going to go ahead and copy it out, though, so you can see it. It's 1/4. Now, it says 1/4 times x, but I meant for that to be 1/4 to the x power if -∞ to -1. You'll notice this one's an interval notation as opposed to inequalities. As I said, either one is fine. It really doesn't matter. It's just about whichever one's more comfortable to you. You can use it. All right, so there we go. I wrote out the function, 1/4 to the x power as opposed to 1/4 times x. And if x is equal to -∞ to -1, -x plus 3, if between -1 and 5, and 2/5 x minus 4 is equal to from 5 to infinity. So let's go ahead, and I'm going to go ahead and just draw out my actual axes here for a second. First things first, let's just break this into pieces. This is all stuff we've done before. It looks scary when you write it out in that big chunk, but it's all manageable. We can do it. So notice first here we have 1/4 to the x power if that's between from -∞ to -1. So that's just an exponential. We did that last unit. We've got a pretty good firm grasp on that. And then we have -x plus 3. That's just a linear with a negative slope. We can handle that as well. And 2/5 x minus 4 from 5 to infinity, that's just another linear. So we have 2 straight lines and an exponential. Now let's go ahead and sketch this out. So I'm expecting it to look something like this. We're going to have an exponential that comes down And then we're going to have a linear. It's got a negative slope. It's going to come down kind of like that. And then we're going to go up again with something that doesn't quite have as severe of a slope. I think it's going to look something like that. I connected all the dots here. That might not be the case, but I'll give you a hint. In this case, they're all connected together. I did set that up on purpose to contrast with the first problem we did. So now let's go ahead and identify our changing points and then sketch them in. So I'm seeing that we've got negative infinity and infinity, but those are just the endpoints. We don't really worry that much about them. They get turned into arrows. It appears to be changing at -1 and 5. I'm just looking at those numbers and just seeing what's there. So let's go ahead and we'll put in our dotted lines at -1 and at 1, 2, 3, 4, 5. Put our dotted line there as well. Okay, so now I put in my lines, figured out our changing points. Now let's figure out about which functions we care about where. So the 1/4 to the x power, we only care about that from negative infinity to -1, which is this right over here. We only care about the negative x plus 3 in between -1 and 5. And we only care about the 2/5 x minus 4 between 5 and infinity. Okay, so now let's go about graphing each of these in turn. We know that 1/4 to the 0 power is going to be 1. So there's the start of our exponential. I'm going to kind of go ahead and do a dotted line. It's going to go all up to 4 and then skyrocket from there. I'm going to exaggerate it a little bit just for clarity. And so there's our exponential function that I've graphed. Now let's go ahead and graph our negative x plus 3. So we start here at 3, and our slope is -1, so we go over 1, down 1, over 1, down 1, and so on, and so forth, to get our straight line. We only care about that one from there to there. Now let's go ahead to our next one. 2/5 x minus 4. So we start down here at -4. We rise to, run 5, rise to, and run 5. Now you'll notice we only care about this particular function, the 2/5 x minus 4, on the right-hand side of this line. So we're only going to connect the dots there, and then that's going to go off for infinity. So it's close to our initial picture, and it's all connected together, and it flows fairly nicely. Since it's all connected together, we don't have to worry that much about the endpoints. However, you'll notice they belong to the right-hand side for all of them. So that's kind of what that's going to be like. All right. Let's go ahead and look at the next problem on the back. It's write the system of equations associated with the following graphs. Assume the graph to the right has the endpoints. Hint, for this one there will be 2 equations. So I'm going to go ahead and sketch out that graph really quick. All right, we have a critical point at 1, -3, and it's going up, just like this. And our other part comes down to like 1/2, right there. And it's gonna go up, just like that. So we're starting with the picture, and we want to figure out what the system of equations associated with it is. Okay? So first things first, we just have to name it. This could be whatever you want, so I'd probably just stick with f of x. And we go ahead and do our curly brackets. We are told from the setup that there's going to be 2 equations here, which makes sense to me because right now when I'm just looking at it, I'm seeing the exponential line and what appears to be a straight line. So that makes sense to me, okay? Now it's customary that when you do this to start from the left and go to the right when you're writing out these equations. You'll notice I did that in all of the previous examples. So let's go ahead and start at the left and work our way to the right. So the first function we hit is this exponential function. You'll notice we have our y-intercept at 1, which to me says that there's not a plus or minus on the end of it. And as we go over 1, we go down 1/2, which to me says that this is going to be a decay exponential function, specifically 1/2 to the x power. All right. It's kind of tricky sometimes to figure out what kind of exponential function it is. So when in doubt, just move over 1 and see how much you're going down. And that's going to tell you what kind of function it is. Also know that I'm not going to give you particularly tricky functions to figure out. Like I'm not going to give you things with fractions or decimals and critical roles, other than maybe a decay exponential value there. Keep it fairly straightforward. I'm not trying to trick you. All right, so now that we figured out the exponential equation, let's go look at this equation. Now it doesn't cross the y-axis, so we don't have a y-intercept. But if it did, we can put in the dotted line and imagine that it does. It appears to be crossing the y-intercept at -4. All right, so now we have the y-intercept. To finish out our y equals mx plus b linear formula, we need to figure out what the slope is. Well, it appears to be crossing right there at that point at 4. So we can figure out what the slope is. We're going to figure out our rise, 1, 2, 3, and our run, 1, 2, 3. So that's going to be 3 over 3, or 1. So we have 1x minus 4. Those are our two equations for the two different parts of the function. Now, let's go ahead and figure out our critical points. Where are we changing? We only are changing at one place, and that's at 1. We care about the exponential part between -infinity to 1, and we care about the linear part from 1 to infinity. I'm going to go ahead and write those in interval notation. You don't have to write them both ways, but I just want to make it as clear as possible. So we'd never put a hard bracket around -infinity, and that's going up all the way to 1, soft bracket, and we're going from 1 to infinity. Now we have to make sure that we include 1 somewhere. The problem says assume that the graph to the right, which in this case is the linear graph, includes the 1. So we'll go ahead and put our equal there and turn that into a hard bracket. Okay? Now let's go ahead and talk about number 3 on the backside. Create a piecewise function with a semicircle, a horizontal line, and an exponential function. It should also have no x-intercepts. You do not need to write the system of equations used. This is the kind of problem that I give you sometimes, where after you do it, you'll be like, that's it? That's what you're asking me to do? It's a fairly straightforward thing that I'm asking you to do, really, and it's the kind of thing where there are going to be lots of right answers. So don't be afraid of what you're doing. Just kind of figure out what it's asking. So it's asking for a semicircle, a horizontal line, and an exponential. And no x-intercepts. So from there, we don't have to include a system of equations, so you can kind of just draw something. So we could put a semicircle here, and then a horizontal line, and then have it pick up into a growth exponential like that. That would work. Or you could do it in a different order. Maybe we'll end with the exponential, and then do the semicircle, and then have it go into a straight line like that. Once again, no x-intercepts, so that would work too. We could have the semicircle go the other way, and exponential for a while, and then flatten out into a horizontal line. That would work, so long as there are no overlaps and no vertical lines. You're good. Let me know if you have additional questions.